Students, in today's class we are going to see about fluid properties, viscosity, compressibility, vapor pressure, surface tension and capillarity. So what is viscosity of a fluid? Viscosity of a fluid is a property which has cohesion and interaction between molecules, which offers resistance to the flow of liquid, and it has small shear deformation. Different fluids deform at different rates under the same shear stress. Fluid with a high viscosity, such as syrup, deforms more slowly than fluid with a low viscosity, such as water. All fluids are viscous. Newtonian fluids obey the linear relationship given by Newton's law of viscosity. Newton's law of viscosity is nothing but tau is equal to mu into dou u by dou y. So if you take a profile of a fluid which is flowing through a fixed pipe, each layer of the fluid has a velocity of u, and the adjacent layer will have some shear stress on it, that is mu. The no slip conditions, velocity no at the wall is zero relative at the wall. This is the characteristics of all viscous fluid. Then the shear stress is proportional to the slope of the velocity profile and is greatest at the wall. Coefficient of dynamic viscosity. So the tau shear stress is directly proportional to dou u by dou y. Dou u is the change in velocity, dou y is the change in distance of the fluid. So if we want to remove the proportionality sign, so we are expressing as dynamic viscosity mu. So dynamic viscosity mu is equal to, from equation 1, it is tau is equal to dou u by dou y. So shear stress can also be calculated using force per unit area divided by velocity by change in distance. Unit of viscosity is Newton second per meter square, where 10 poise is equal to 1 kg per meter per second. Typical value of dynamic viscosity of water is 1.14 into 10 power minus 3 kg per meter per second. For mercury, it is 1.552 kg per meter per second. Kinematic viscosity, nu. It is defined as the ratio of dynamic viscosity to mass density. Units meter square per second, and it is expressed in strokes. So 1 meter square per second is equal to 10 power 4 strokes. Typical values for water is 1.14 into 10 power minus 6. For mercury, it is 1.145 into 10 power minus 4. Paraffin oil, 2.375 into 10 power minus 3. So we'll see a numerical problem. The space between two square flat parallel plates is filled with oil. Each side of the plate is 720 mm. The thickness of oil is 15 mm. The upper plate, which moves at 3 meter per second, requires a force of 120 Newton to maintain the speed. Determine the dynamic viscosity of the fluid and the kinematic viscosity of oil if the specific gravity of oil is 0.95. Each side of the plate is given as 720 mm. So it is converted to meter into 10 power minus 3. So it is 0.72 meter. The thickness of oil film is 15 mm. So this is also converted into meter into 10 power minus 3. So 0.015 meter. and the velocity of upper plate is given as 3 meter per second. Therefore, change in velocity between the plate dou or du is equal to T2 minus T1. So T1 is 0, T2 is 3. 3 minus 0 is 3 meter per second. The force required on upper plate or shear force is 120 Newton. So therefore, shear stress is equal to force by area. So force is already given 120. So it is a square plate and the area is 0.72 into 0.72. So if you calculate shear stress, it is 231.5 Newton per meter square. Next is dynamic viscosity mu. So we know the relationship between the shear stress, dynamic viscosity, and change in velocity with respect to distance. So we know the shear stress. We know the dou u by dou y, du by dy. So we can find the dynamic viscosity. Mu is equal to 1.16 Newton second per meter square. Then they have asked to find the kinematic viscosity if the specific gravity is given. So they have given the weight density of oil, W is equal to 0.95 into 9.81 kilonewton per meter cube. So Newton per meter cube, 9320 Newton per meter cube. And we know the relation weight density of the oil is equal to rho into G. So we need mass density of the oil. So rho is equal to W by G. So we know W and G also. So it is 950 kg per meter cube. Mu of kinematic viscosity, mu is equal to mu by rho. So we know both mu and rho. So it is 0.0122 meter square per second. So what are the different causes of viscosity in fluids? Viscosity in gases. The molecules of gases are only weakly kept in positions by molecular cohesion as they are so far apart and adjacent layers move by each other. There is a continuous exchange of molecules. If temperature of a gas increases, the momentum exchange between layers will increase, thus increasing viscosity. Viscosity in liquids. There is some molecular interchange between adjacent layers in liquids, but as the molecules are so much closer than in gases, the cohesive forces hold the molecules in place much more rigidly. This cohesive plays an important role in the viscosity of the liquids. Increasing the temperature of fluid reduces the cohesive force and increases the molecular interchange. So how we derive the Newton's law of viscosity? Considering a 3D rectangular element of fluid like that in the figure below, the fluid element, the shear force F acts on the area on the top of the element. This area is given by A is equal to ds into dx. We can thus calculate shear stress, which is equal to force per unit area. Shear stress is equal to force per unit area. The deformation which this shear stress causes is measured by the size of the angle F and is known as shear strain. So it has been experimentally found that the rate of shear strain is shear stress per unit time is directly proportional to shear stress. If the particle at point E in the above figure moves under the shear stress to point E, it takes time t to get there. It moves the distance x. For all deformation, we can write shear strain theta is equal to x by y. Rate of shear strain is equal to theta by t, u by v, y. Using the experimental result that shear stress is proportional to rate of shear strain, then tau is equal to constant into u by v. The term u by v is a change in velocity with y with respect to y, or the velocity gradient may be written in the different form du by dy. The constant of proportionality is known as the dynamic viscosity of the fluid, giving tau is equal to mu into du by dy. Newton's law of viscosity. Surface tension. A fluid being unable to expand freely will form an interface with a second liquid or gas. Thus, the coercive force between liquid molecules are responsible for the phenomenon such as surface tension. Vapor pressure is the pressure at which a liquid boils and it is equilibrium with its own vapor. When the liquid pressure is dropped below the vapor pressure due to a flow phenomenon, then we call the process as cavitation. The dimensionless parameter describing flow induced boiling is called cavitation number. And the effect of surface tension is capillarity, rise and fall. If you take a beaker and if you insert a tube which is opened both sides, the tube containing water exhibits positive capillary rise, where the water adheres to the sides of the tube, causing the fluid to rise slightly. The capillary fall. The tube containing mercury exhibits negative capillary rise. The fluid is drawn away from the walls of the tube, causing the fluid to sink. So from the figure you can see, so the water is filled in a beaker and a tube is inserted, so that we can see there is some rise in the fluid flow and the fluid is filled. That rise is called capillary rise. And if a beaker is filled with mercury, then it is capillary fall is formed. So we'll solve a problem on capillary effect. Calculate the capillary effect in millimeters in a glass tube of 4 mm diameter when immersed in water and mercury. Temperature of the liquid is 20 degrees Celsius and the values of surface tension of water and mercury at 20 degrees Celsius in contact with air are 0.0735 Newton per meter and 0.51 Newton per meter respectively. The contact angle for water theta is equal to 0 degree. For mercury it is 130 degree. Take specific weight of water at 20 degrees Celsius as equal to 9790 Newton per meter cube. So surface tension is denoted by sigma. Sigma is equal to 4 H is equal to 4 sigma cos theta by rho GD. So by using that formula we can find the rise in capillary. So surface tension at 20 degrees Celsius for water and mercury is given and specific weight of the water is also given. From that we can find the density of the liquid. So capillary effect is 4 sigma cos theta by rho GD, or it can be written as WT. So specific weight is directly given, so you can directly substitute. So it is equal to cos 0 is 1, 7.51 mm rise. Capillary effect for mercury, so it's cos 130 degree. So and the specific density of specific gravity of mercury is 13.6, 9.81. Thank you.